Welcome to my second Bioforce 60 video essay on membrane potential, action potentials, and myelin with neurons. So to begin, let's discuss resting membrane potential. So the resting membrane potential is the resting electrical charge of the cell membrane, and this is caused by electrochemical gradients in the cell. So there's three main contributors to the RMP. Number one is potassium leak channels. So there's always more potassium inside the cell than outside the cell in a physiologically healthy human. So what happens is the cell has these open potassium leak channels that allows that potassium to leave the cell, and that positive charge is leaving the cell, but the negative charge stays behind. And this separation of charge here creates a negative resting membrane potential of about minus 70 millivolts. We can measure this. So imagine we have a container of solution here separated by a membrane that is only permeable to positive charge. So what's going to happen is the positive charge, since it has that membrane it can go through, is going to diffuse down its concentration gradient from high concentration to low concentration. But since it's only permeable to that positive charge, it's going to leave behind its negative counterpart, and it's going to produce a positive charge on the other side of the membrane and a negative charge on the side that it came from. So what this establishes is the electrochemical gradient. So the chemical gradient is just the concentration gradient. The solute goes from a high concentration to a low concentration. But there's an electrical gradient created here when this charge starts to cross this membrane, because now we have this negative charge trying to pull the positive charge back. So we have two opposing forces. They're playing tug of war. We've got negative charges that are trying to summon the potassium back into the cell, and we've got the concentration gradient that's trying to push the potassium outside of the cell. So what happens here is we reach a state of equilibrium where there is a net no movement of ions. But since we do have a concentration gradient of potassium leaving the cell, it does leave behind negative charges, and so we get a RMP from that. The second contributor is the sodium potassium pump. So this is a protein carrier in the cell membrane that pumps out 3 sodiums for every 2 potassium ions that it brings in. So this establishes the chemical gradient that we need to even have a resting membrane potential in the first place. But what's causing the RMP is not that there's more positive on the inside than outside. It's what happens when those charges get separated by the potassium leak channels, right? So this is a relatively small contributor to the cell's resting membrane potential, but it mainly contributes by establishing the concentration gradients of potassium being more plentiful inside the cell than outside the cell. And then we've got the negatively charged proteins that we find in the cell that are mostly negatively charged, so that adds to our negative resting membrane potential. So the three of these things together, these potassium leak channels, the sodium potassium pump, and the negatively charged proteins, work together to create a resting membrane potential, which is a resting electrical charge of the membrane caused by electrochemical gradients. Let's see. So next, what properties and characteristics of the cell membrane account for the resting membrane potential's development? So the characteristics of the cell membrane that account for the resting membrane potential's development is the fact that the cell membrane is made up of phospholipids. So these have a polar head and a non-polar fatty acid tail. So what happens is the tails come together, the heads oppose, and really nothing can cross this membrane other than gases like CO2 and O2. It's really hard for ions to cross as well as water. So we need facilitated diffusion for that to happen. And so because of this, we can establish, because of these phospholipid heads, the polar head, and because of this cell membrane that's comprised of phospholipids, we can create electrochemical gradients where the cell membrane is permeable to some ions at some times, and then different ions at other times. And we can control the amount in which ions leave and enter the cell. All right, what's my next question? So what conditions or factors affect the resting membrane potential's magnitude? So we have a couple conditions here that can affect the resting membrane potential's magnitude. So this is basically going to depend on, we can change the magnitude of the cell membrane, resting membrane potential, by altering the concentration of ions. So we can change that concentration gradient. So for example, with hyperkalemia, normally we have a lot more, normally in the cell under normal conditions, we have a lot more potassium inside than outside the cell. With hyperkalemia, we have more potassium outside the cell than inside. There's still more inside though, there's just more than usual outside. But what this does is it makes the concentration gradient less steep, less pronounced. So potassium is less likely to leave the cell, which is going to result in an abnormal accumulation of positive ions, potassium ions inside the cell, which is going to overall give us a more positive resting membrane potential. Additionally, we can have hypokalemia, which is just a lower amount of potassium than usual outside the cell. And this is going to drastically exaggerate the concentration gradient that we already have. So potassium is going to really want to leave the cell now. And so this is going to result in a more negative resting membrane potential because we have more positive ions leaving the cell. All right, and then what's my next question here? One second. Just skip ahead this part if you want to. Okay, so now we're going to have a brief discussion of the Nernst equation and then driving force. So the Nernst equation here is going to give us our equilibrium potential, which is the voltage where the chemical gradient is equal to the electrical gradient that I talked about earlier with this diagram here, where there's a net zero movement of ions across the membrane due to the opposing forces of the chemical and electrical gradient. So the Nernst equation is going to tell us this value, and it's equal to negative 61.5 over Z times the log of the ion concentration inside the cell divided by the ion concentration outside of the cell. So the negative 61.5 is just a constant that represents normal body conditions like temperature. And then Z is going to be the charge of our ion. And so we can plug the values in that we have for, say, sodium. So sodium's a positive charge, so we'd put positive 1 there. And then we would just put our concentrations in, and that would tell us the equilibrium potential for sodium. However, the Nernst equation does not account for other ions or the permeability of the membrane, and therefore it is an unreliable measure of the true resting membrane potential, but it's useful to know. So for driving force is basically the force of which ions want to enter the membrane. So this is calculated by taking the equilibrium potential that we calculated in the Nernst equation and subtracting the voltage of the membrane. And this is going to give us our driving force. So ions like sodium have a really high driving force into the cell due to the high concentration of them outside compared to inside the cell. So driving force is just how badly that ion wants to enter into the cell. All right, 1 second here. Let me go on to the next question. Let's move over to my next whiteboard. So part 2 of the essay, we're going to discuss the action potential. So I'm going to list its characteristics. So the action potential is how we transmit synapses through nerves. Right? It all depends on this here. So in our graph here, we have -70 representing the resting membrane potential, -55 millivolts representing the threshold that it takes to cause an action potential, +30 represents the depolarization that occurs during an action potential. So what happens here is we have things called graded potentials, and this is when the voltage of the membrane changes due to maybe an influx or outflux of ions, influx or efflux, but we don't quite reach threshold. Now we can reach threshold if we have numerous graded potentials added together, we'll reach threshold. But a graded potential is just a change in the membrane voltage that does not occur, that does not result in an actual action potential. Let's see. All right, so describe the events that take place during a typical action potential. So what will happen is we'll have an influx of ions into the cell that changes the resting membrane potential, which is going to cross the threshold, the action potential threshold. So what happens here is once we cross that threshold, voltage-gated sodium channels that are sensitive to this change are going to open up for just a moment, just a millisecond or so. And we're going to have an influx of sodium ions that's going to rapidly depolarize the cell resting membrane potential. And then what's going to happen is that in response to this, we need to repolarize, right? So potassium voltage-gated channels are going to sense this depolarization. They're going to open up, and then potassium is going to exit the cell at a higher rate than usual, and that's going to result in a reaccumulation of negative charges inside the cell. And then we're going to repolarize, and we're even going to dip below resting membrane potential a little bit here, because some of these potassium channels are going to be open, and then we're also going to have those leak channels open, right? So some of these potassium channels are still going to be open, and our leak channels are almost always open. So that's going to result in hyperpolarization. And then we'll return to RMP once those channels close up. So we've got what we call the absolute refractory period, is the time that a second action potential cannot occur. And then we have the relative refractory period, which is where a second action potential could occur, but it would require a greater stimulus than it initially took, because we have this little dip down below the initial resting membrane potential. You know, we've hyperpolarized, right? So then, so the graded potential is a smaller change in the resting membrane potential, and the action potential is a major one that is initiated by a graded potential that crosses threshold. So now let's move on to capacitance and length constant here. So capacitance is reliant upon conductance, which is the ability of ions to cross the cell, and capacitance is the separation of charge for volt per volt. So our equation here is capacitance equals the charge separation divided by the voltage, right? And then for our length constant, our equation for this is length constant is equal to the square root of the membrane resistance divided by the internal resistance. So the membrane resistance is the resistance against a ion entering into the cell, crossing the cell membrane. And the internal resistance is basically the resistance that an action potential signal is going to face due to things like proteins inside the cell, charge as a result of high capacitance. And so what happens here is we have our neuron cell, our cell body, got our little axon hillock there where our action potential happens, and it's going to create a buon, a big signal. So what this looks like on the nerve is that we have a lot of accumulation of positive charge and negative charge there. And then what's happening is because there's not, see, these charges are all very close together. And so they can get closer together because they're being attracted by that opposing charge on the other side of the membrane. But what happens is if we add something non-polar like myelin to the nerve, which is basically like a lipid coating, then that capacitance is going to decrease, and our signal will be able to travel more freely because there's not as much interference from high capacitance there. So what happens is those charges get farther apart, they're going to interfere less. And then internal resistance would be like if we had a lot of protein in there inside of the axon that would interfere with the signal, or if we had like a narrower axon body. So myelin is going to decrease our capacitance, and it is going to increase our length constant. And we want a high length constant so that that signal can travel all the way down the nerve and trigger the next synapse. It's important that this signal can travel uninterrupted by high capacitance or a lot of internal resistance. So myelin helps us to overcome those things. All right, and that concludes my video essay number 2. Thanks for watching.